Great. Technical issues solved. Now we have Simon Burton, who's going to talk about categorified path calculus.
Right. Thanks for coming along. Right, so this is a lot of string diagram stuff that I'll be talking about. And I forgot, really was thinking about this more again today. There's really a motivation zero, which is no letters. This is mathematics without letters. So I feel like the part of my brain that does mathematics is not the part of my brain that is the verbal part. So whenever I see an equation with an A somewhere and an A somewhere else there, like, why don't we just draw a line between those two? Like the A label is just trying to identify two different locations. So the idea is we're just going to draw a line between those two locations and do it that way rather than, yeah. So I find this typical mathematical syntax very confusing. So that's motivation zero. Okay, but motivation one is, well, we have these string diagrams for the tensor product. This is a typical kind of a trace in a monoidal category that you might want to do, but how do we do if we want another monoidal product? And I think of vector spaces a lot, so how do we do direct sum as well? Motivation two comes from quantum physics, and so this is about amplitudes, and I guess what I really want to say is, what is an amplitude counting? Because an amplitude is a number. So what is it counting? And the answer, or one answer to this is, you can find this stuff in Feynman's physics lectures, volume 3. This is how he introduces quantum physics as a kind of path counting. And his idea is that you have a particle going from some source to some x, and this is the equation that he writes here, that if there's two different ways, two different holes that it can go through, then the amplitude, the total amplitude you get is from adding up the two different possible ways, because there's two paths here. And I've got a kind of picture here of how this is going to grow. Another example, just two possible ways and three possible ways. And then there's another rule for if a particle does something and then it has to do something else, then you multiply the amplitudes for those two processes. And that's really in terms of path counting, that's this kind of serial composition of paths. And there's a very nice string diagram calculus for these kinds of things. I've drawn some examples here. Have people seen this kind of stuff before? Have some references as well down here. It's kind of amazing to me that this is really on the nose what Feynman was talking about in his 1960s lecture notes, but he doesn't mention path counting at all. And even though he's famous for like Feynman diagrams, and I guess this is how he was thinking about quantum in terms of particles going through particle accelerators and this kind of stuff. So that's where his brain was. Actually, I'd really like to go back to the Feynman lectures and see if I can find any tensor product stuff there. I don't know, because this path counting stuff is more about the additive structure of quantum. So Feynman doesn't talk about entanglement, unfortunately, because it hadn't been invented there or something. But then really, like, it takes him until chapter 8 before he starts talking about these weird unfinished quantities. These are like half bracket things. This is called a ket. This is called a bra. And he says these are just temporary distractions from on our way to actually working out what an amplitude is. So don't freak out. But this is Feynman's way of like sneaking in linear algebra through the back door. Like I don't think he even says linear algebra anywhere in his textbook. And in terms of string diagrams, I've got a couple of examples here. So a string diagram with one, and my diagrams are going this way. So there's one input and two outputs. Is this matrix? This is what how Feynman would do it. And this one has two inputs and one output. So it looks like that matrix. And please interrupt me, any questions?
Why right to left?
Because I'm left-handed.
Oh.
There's one answer, but the other answer is like, it's the algebraic direction, and I put my matrices under my string diagrams, and so I get very confused if they don't agree. So. Okay, so I've got some more calculations here, and we can see like how all right, so that's like a bracket here and a ket bra thing here. And I'm drawing these diagrams slightly slanty because I'm thinking of these as actually going into the board. So this is the direct sum direction and the composition direction. And right, so when I direct sum these, when I just stack these in parallel, these string diagrams, I'm taking the direct sum of matrices. Okay, so that was a very quick introduction. And right, and some weird stuff happens with zero matrices with no rows or columns can have matrices with no columns can have rows and vice versa. So I put these extra numbers here to say like this matrix has got where is it? Is no rows but one column. So right, so it can eat something, but nothing comes out here. So then you can do these kinds of calculations when you direct sum with these weird empty matrices to get stuff like this, and this is a unit equation for a monoid. And this is where the path calculus takes off, and you start thinking about monoids and comonoids and units and co-units. And you write down all these equations, and then the punchline to all this is that you recover your diagram calculus recovers the theory of matrices with natural number entries. So what do? We just replace natural numbers with a category, and I'm going to just start with the category of finite dimensional vector spaces. So going the other way is going to be, you just take the dimension of your thing to get, so we know that vector spaces, right, we're adding and multiplying vector spaces now, and just like we were adding and multiplying natural numbers, and we're going to make matrices of these vector spaces. And we're going to extrude our string diagrams now. I've been saving the third dimension for the categorified. And so these are supposed to be the same string diagrams as before, just categorified. And here are some calculations these are the same calculations I just showed you with natural numbers. I'm just doing it. Did I say what I was? So I is just like some, maybe I should say that. So I is like some one-dimensional vector space, and O or zero is some zero-dimensional vector space. So that's me fooling around with i's, and that's the unit. What did I call it? The unit equation categorified. But what's going on here? This is not an equation anymore. Because this, strictly speaking, this weirdo vector space is not the same as this one. They're isomorphic. So there's some there's some extra structure here going on. It tells you how to recover your one-dimensional vector space from all this junk over here. And well, we can actually start to write this extra structure as these are these two cells. And this really is just, we took the equation that we had before. I was just writing this as an equation before in path calculus. And I'm just replacing this equal sign with a two cell and just kind of coning, this is called coning, just extruding out to where I start and where I end here. So that's a typical categorification trick, is you replace equations by morphisms. This is an isomorphism, so we should be able to go backwards now. And so this is what it means to be an isomorphism. We just draw the inverse string diagram upside down, and right, there's no letters here. Yeah, and it's all right. It looks kind of, you can get the groove here. You can if you have a little flap here, you can just eliminate it like that, or you could drag two flaps together to get this thing. So going back to the path calculus, Feynman would be not quite agreeing with the way that I talked about Browse and Katz, because he was using complex numbers, and so maybe that's what we should do as well, is try to use some ring, semi-ring or rig, and decorate our paths with elements from the semi-ring. And you can do that, and there's a bunch of rules for how this works. And the punchline here is that you'll recover the theory of matrices over your semi-ring from this calculus with decorated paths. And so what is this going to look like when we categorify this stuff now? So how am I going to explain this? So right, I'm gonna do the same thing that I did before. I'm gonna put a two cell here, and I'm gonna extrude this red guy and this blue guy and the green guy. So it's going to be this kind of morphism here is going to become this equation is going to become a two cell. Yeah, and so in general, what we do here is not just finite dimensional vector spaces, but this stuff here is going to be called a bimonoidal category. So C is this bimonoidal category. So it has two monoidal structures, and the important thing is that the multiplication distributes over the addition. And there's all this stuff that goes on and on. But fortunately, someone has worked all this out in extreme detail, and it's actually two people, Johnson and Yao. So a lot of what I do with the string diagrams is based on what these guys have done in precise fashion, and they really show how to do these matrices over a bimonoidal category, and how there's no string diagrams in what they've written. So I really felt the need to see what these things actually look like. Okay, so here we go. This is like a direct sum of two one cells, and I'm using the square direct sum now for the round direct sum is going to be the one inside the category. So the square direct sum is the one of direct sum of matrices. And that's how it looks for two cell. What am I doing here? Direct sum of two cells. And so what's happening here is that the components of the matrix are So we start off with this map F is going from A to B. So this thing is in the underlying category, the underlying bimodal category C. And here you can see it's just component wise. This is what the two cells do. They component wise map I ran out of words. Just give up on that. Wait, I'm trying to draw pictures so I don't have to explain this. So, right, that's horizontal composition. What else have I got here? This is a more general morphism here. You can see I'm packaging up a whole lot of morphisms from C in this matrix form. And you can see that this is like a 3x2 matrix. It's worth meditating on this for a little while. Yeah, so horizontal multiplication, you're really using matrix product, and then the vertical multiplication, you're just composing these guys, these original functions, morphisms from C. Up the page. Yeah, some people are nodding, that's great. Right, so before we had this equation in the path calculus. You have something in your ring there. Wait, screw this up. Something in your ring there can be copied over like that, and these are equal. So in the categorified path calculus, again, this becomes a two-cell. And you to actually figure out what is this thing here, you use all the funky bimodal isomorphisms and blah 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 to actually work this out, right? Because yeah, I mean, yeah. So that's where you get that isomorphism from. But that's the picture of it, and it's an isomorphism. So what does it look like when you draw the isomorphism equations? Well, it's this, I call these pulling equations. So you can pull a string onto a double sheet like that, or or pull it off from a single sheet like that. And I guess co-pulling is when the double sheet is on the other side.
Pushing.
Could be called pushing, but we're category heroes, so we just do code whenever we can.
Wait, I can't be called pushing.
Code pushing. Yeah, well, obviously there's some degree of freedom here that we okay.
Oh.
Right, and this thing is natural, so you can what are we doing? Pulling or pushing? I forgot. So we can pull this guy up onto the two sheets like that. Now, the cool thing about this stuff is totally backwards compatible. Hey, so whatever you're used to doing with your monoidal categories, fine, it just lives on sheets in the same way. You can keep doing that stuff. You just have these multiple layers now. What else am I saying? Right, so I feel like this needs a better name, and maybe it's related to the microcosm principle, but this is a very general categorical idea that for Feynman, he was like annoyed by these bras and kets as like these half-finished equations that didn't mean anything, but you could recover the amplitudes that did mean something as like one input, one output, whatever craziness happens in the middle. So this is the real stuff, is the amplitudes. And right, so the string diagrams with one input and one output give you these scalars. So you've got all this fancy machinery, but by looking down at just some of the diagrams, you get back to reality. You recover your original ring structure. And the same thing happens with the categorified path calculus, that you think about diagrams with one input sheet and one output sheet. And what is supported on those diagrams is this Tom category. It's the same as the original category that you started off with. So let me just add a bit more structure to the underlying category, and I'm going to say that now I want my plus to be byproduct. So I can do, so my underlying category has matrices, and then I'm going to do those with round brackets. So I get big morphisms that look like this now. So this is a morphism in my underlying category, but this is what it looks like. So I get these caps and cups, and these other caps and cups, and anyone wants me to dwell on this, say, tell me, let me know. And magically, you get that these two one cells are ambidextrous adjoints. And what that means is you get all these snake equations. And this is what these things look like. There's a whole bunch more variations where it's like two sheets on the left and one sheet on the right. And this is how you get a Frobenius algebra. And the multiplication, this is the, wait, I'm going off the page here. So this is the multiplication. And this is, wait, no. This is, wait, is that right? Well, that's the multiplication. That's the co-multiplication. Yeah. So multiplication is like comparing which sheets you're on and making sure they're the same. Co-multiplication is kind of copy. So it's copy and compare. It also turns out to be special, and you can, it's not too hard to show that. And it's showing that it's symmetric. This is much more tricky to show using these string diagrams, because I think you're going to need a lot of sheets, and I haven't actually, this is maybe where you need to think work symbolically to figure that out. But yeah, this is what Jamie Vickery calls a classical bit. And weirdly, I think this means that there's another guy on this one. Because it's an ambidextrous adjoint, so there must be another one on the reversed. This is another Frobenius. Do you know what this is? I don't even know what to call it. It's like a covert. Yeah. Right. So now I'm going to talk about categorical quantum mechanics, and this is really a lot about the dagger, which is when your category has morphisms and they're not sure which way they're going. So the thing is, like whenever you build a structure in your mathematics and there's an ambiguity there, the way you take care of that ambiguity is you find that there's a group or a symmetry there. So you use group theory to take away structure. It's like a general Kleinian geometry principle. So that's what dagger categories are. They have this tiny group theoretic. You build your category, but then you're like, oh no, I've gone too far, and then you want to take a bit of structure back, and you do that with the dagger. So it gives you this ability to reverse the direction of morphisms. So for this two categorical stuff, we're just going to reflect. What is this? Up and down gets reflected. And these are pictures of measurement. So I've got my A here is a two-dimensional vector space, unitary vector space. And all I'm doing is, well, somehow magically it spews out these two sheets. Now, is anyone thinking like parallel universes and multiverse yet? So, this is totally what this is. Right, and, okay, so I didn't say what, so unitary, unitary two cells is that the dagger of the two cells, it's inverse, so that's what unitary means. So these are all, so cubic measurement is supposed to be unitary, so you can undo it as well. And then control operation is, well, we've got this classical, this multiverse over here, and in one universe we're doing U1, and in another universe we're doing U2. And teleportation, this is, we're going to, I've got an N here, so this means like N sheets here. So I'm doing a measurement, I'm preparing a entangled state here, I'm measuring this guy, and then there's some control operation up here, and it's supposed to be, I'm supposed to be able to just bend the diagram around like this. And there's one more bit of trickery, this unitary error basis. So this is going to be my measurement up here. This is what I'm going to use here. Is this big guy. And then, so this is my teleportation protocol. That's my measurement is over here. And this is my control operation here. And you can see what's going to happen here is I'm just going to pull this red string using the pulling or pushing or whatever onto the different universes over here. And then the U's are going to undo each other. And then I can reverse the pulling operation, and then I'll just end up with some classical bit. So that's how it goes. I pull the red strings onto the multiverse, and then the U's cancel each other out, and then I can pull the multiverse back out over here, and I'm done. So this is my conclusion slide, and I think the only thing I didn't talk about today is the weak structure, and that's kind of interesting as well. But one other thing I'll mention is last year I gave a talk at the Psycho conference about this, how I make these diagrams. So that's it. Thank you.
Great. So any questions? Yes.
Thanks for the talk.
Hey.
I remember when I initially read Jamie and David Rodo's stuff on this, I didn't realize there was this connection to just services for weight categories, because the way that they typeset the diagrams is not as beautiful.
Well, okay, so right, so Vickery's stuff. So he has these three-dimensional sheet diagrams as well, and so they are. He uses let me draw it as box times. So this is the big difference between his stuff and current, what I've been telling you about today is box plus. So this, the Vickery stuff is actually way more weirder. I'm not, it's actually much simpler what I'm doing here. But, yeah. I don't know if that was at all what you wanted to ask.
No, that was just what I want to ask you is, we seen this other paper by Jamie, this previous sim, where they do this thing where they look at a linearly distributed category with these proof nets, where you have a tensor and bar connectors, but then they show that if you categorify things properly, then you have this kind of categorified Frobenius solver, such that when you take the projection back down, you get proof nets for linearly distributed category.
Sounds great.
I was just wondering if you could project this down and get some sort of two-dimensional graphical calculus for three categories, so you don't have to on a whiteboard draw three-dimensional.
Yeah, well, I think there's this other stuff called tape diagrams, and I think that might be what that is. And there's other guys doing this stuff with linear optics as well. They're just fooling around with all these different, I think that there is actually a lot of that stuff going on. Yeah. Well, I'm kind of happy sticking with 3 dimensions here. So, yeah, that's.
Any other questions? Yes.
Does any little possible connection with the conformal theory?
Can you say more about that conformal field theory?
It's just that your diagram seems to be similar to what you do with the whole.
Yeah, I mean, right. Yeah, yeah,
Doesn't seem
yeah. It's all, yeah. I'm sure there's connections. Yeah, yeah, yeah. Yeah. I mean, these string diagrams, they seem to show up in lots of different contexts, and it's like they mean different things in different areas, and it's wild. Yeah. So,
First question here.
Mine's kind of what you can ask is like, can you remove the structure again, purely topological thing here, and then is that then some category of coordinates?
oh, right, like the walking, whatever, blah blah blah. Yeah, yeah. Sounds good. Yeah.
So you said earlier that you were happy with dimension 3, so I almost feel kind of think about asking this question, but there's also work that Nick Gursky did on braided monoidal 2 categories, and this kind of
Yeah.
analogous surface diagrams there, you had 2-dimensional sheets braiding past one another in 4-dimensional space. And I was reminded in this talk that if you take a 3-dimensional projection of that, so that's the 2-dimensional things in 4-dimensional space, you take a 3-dimensional projection of that, it looks very similar to what you had here. I wonder whether there's a known relationship there, because distribution is not exactly the Ekman-Hilton argument, but somewhat related.
Yeah. I'd like to. I really need to study Gursky's work for sure. Yeah.
Yes.
So when you first talked about category, you talked about extending categories to common dimensional vectors, basically.
Yep.
Just keep going until appropriation.
Probably. Yeah. I mean, this you can see here, like this matrices over a bimonoidal category. It's also bimonoidal, bi-bimonoidal, whatever. So like this thing is it's not going to end. Yeah.
I think that's all we have time for.
Okay.
Although, of course, there's nothing after this, so you can just keep asking. But otherwise, let's thank the speaker again.